Okay. So I think this week we're maybe finishing discussion of the GKR protocol and starting to talk about, I guess, chapter 7, which kind of covers how to combine the GKR protocol with the polynomial commitment scheme and talks about what a polynomial commitment scheme is to get a snark. So hopefully I'm right about that because that's what I was planning to discuss. So yeah, to wrap up the discussion of the GKR protocol, let me, I guess, just remind you that, the prover and verifier agree on a circuit. So here's the inputs to the circuit. And, it's a layered circuit of fan2. So, there are all these gates in the circuit. And each gate, which I'm just drawing as like an almost not visible dot here, is computing addition multiplication over a field. Okay. So on the input, when you evaluate the circuit on the input X, gate by gate, you can evaluate the circuit gate by gate, with which each multiplication gate computing the product of its two inputs and each addition gate computing the sum of its two inputs. And so each gate in the circuit winds up sort of getting assigned a value when you evaluate the circuit and then I guess the book refers to, for each layer of the circuit, it refers to sort of the vector of gate values as, W sub whatever the index of the layer is. So the output, I think we call layer 0. And, there's one layer there's one vector for each layer of the circuit. And then we, sort of conceptually take the multilinear extension of each of these vectors. And remember that entails interpreting the vector really like not as a vector, but as the set of like all of the evaluations of a function over the Boolean hypercube, 0, 1 to the log vector length. Interpreting the vector as like the list of all evaluations of that function. And then any function with such a, domain 0, 1 to the whatever has a multilinear extension. And so at layer I of the circuit, the key equality is that the multilinear extension of sort of the vector of gate values at layer I evaluated at some point, which is, the point that the prover in the previous iteration was forced to make a claim about, then be expressed as a sum over all sort of gate labels for the next layer up. So if Si plus 1 is the number of gates at layer I plus 1, then you're summing over the, binary labels of gates at the preceding layer. And like for simplicity, let's just assume that there's only multiplication gates. So you have this function capturing the wiring of the circuit. Sorry, unfortunately, this whiteboard app picks up not just my pen, but also my finger. I'm not sure how to change that. So you're seeing like stray marks on the screen. But yeah, so this will be Ri dc times Wi plus 1 twiddle of B times Wi plus 1 twiddle of C. I don't know where that red line just came from. Okay, so the iPad only works so well because I also, like, last week when I was using my laptop, I could scroll down the screen. And now when I try to scroll down the screen, it just draws lines I don't want to appear on the screen. So it's a mixed blessing, the iPad.
Does two-finger scrolling work or no?
Yes, it does. Thank you very much. That's great. Okay. Let's see if we can erase some of these straight. Oh, okay. We can't really erase the red line without erasing someone I drew. But at least I can scroll down the screen now. So thank you for that. Okay. So let me try to fill that back in. Yeah. So this was the key equality, that you can express the multilinear extension of the gate values at layer I evaluated at any point. And note that, this is not necessarily in the Boolean hypercube. In fact, with overwhelming probability, it's not in the Boolean hypercube. It's just, a vector with field elements. And sort of, so at that point, like, you cannot interpret this vector. It's like not the label of any gate, right? We're really operating sort of in the multilinear extension here. As soon as you feed into the multilinear extension polynomial non-Boolean values, you're really operating in extension land. You're not just pulling out gate values anymore. And despite that, we have this nice equality where we've expressed the multilinear extension evaluation as this nice sum, which is amenable to an application of the sum check protocol. So, the GKR protocol will wind up applying sum check to the polynomial like g of b comma c defined to be basically just the thing being summed here. So multi of Ri, comma, B, comma, C times Wi plus 1 twiddle of B times Wi plus 1 twiddle of C. Again, I'm assuming here there's only multiplication gates, so I don't have to deal with the add-I twiddle term. Yeah, so it applies the sum check protocol to G. Okay, and at the end of the sum check protocol, so the verifier over the course of that sum check protocol runs in just logarithmic time, like linear in the number of variables being, of this polynomial G being summed. And that's because G has degree only 2 in each variable. So, there's one round for each variable, and in each round, the prover's message is just a degree 2 polynomial. So everything for the verifier is very fast, except at the end of the sum check protocol, the verifier has to evaluate G at a random point. Okay, that requires evaluating, multi at 1 point and Wi plus 1 twiddle at 2 points. And so there's that stray mark again because I didn't use 2 fingers. But anyway, yeah. And then, we don't like the fact that you now have to evaluate Wi plus 1 twiddle at 2 points. So there's a technique covered in the text to sort of reduce 2 points to 1. And by the way, I got a question this week saying that an example of that technique would be nice. And so I just wanted to mention there is a picture and an example of that technique. So that earlier in chapter 4, there's like a self-contained section where that technique is covered in detail. So if you didn't realize that because it wasn't part of the assigned reading, have a look. So I just put a little pointer in to the picture and example in the coverage of the GKR protocol. So yeah, that kind of covers everything, except I wanted to discuss today, the verifier needing to evaluate like multi-twiddle at one randomly chosen. So this is like a subtle issue that arises and basically all snarks. So there, whenever you're giving a snark for circuit satisfiability or R1CS satisfiability or whatever, you always have to like capture the wiring of the circuit somehow. And that wiring is always captured by, some kind of polynomial that encodes the wiring. So for the GKR protocol, it's, this mult-twiddle polynomial, one for each layer. For other snarks, there's typically just a single polynomial capturing the wiring, or maybe, 2 or 3 or something for the entire circuit or R1CS instance or something. So it's sort of an annoying situation to make precise statements about, but basically any circuit or R1CS instance or what have you with repeated structure, these evaluations can just be done very quickly. And that's something I wanted to talk about today. So that's really the main reason I brought up the whiteboard. So let me dive into that. So let me draw a circuit that actually captures a lot of things people do in practice. And I call it data parallel. So it means the circuit consists of like a small like sub computation. I'll call it, C sub. So you kind of do the same thing, the same small thing, but you do it over and over again many times, sort of independently to many different pieces of data. So, the input is sort of chunked up into a small number of pieces, let me call it just, X1, X2, X3, blah, blah, blah. But each Xi here might not be just a single, field element. It might be several field elements or something. And then, so the computation is going to do the same small thing in this data parallel manner, right? And then the results might or might not be aggregated in some way. So there might be some simple aggregation function that the outputs of all the sub-computations feed into, and that spits out your final answer. So, some examples of this, I don't know, let's say you have a Merkle tree, which we haven't discussed Merkle trees in detail before, that they're covered in chapter 7, which is we're scheduled to talk about today. But yeah, a common thing people often want to do, particularly like for ZK rollups and stuff, is there's some Merkle tree and the prover wants to prove that, it knows a bunch of, it says, hey, this is like the data living at a bunch of leaves of the Merkle tree. And like, here's the authentication information for each of these pieces of data. So in that case, like each of these Xi's will be, like the revealed piece of data and the associated authentication information for that data. And then C sub is just going to check for each of them that the authentication information is valid. And what that means, and again, we're going to talk about Merkle trees, I think, a little more later, shortly. But a Merkle tree, consists of like it's like a commitment to a bunch of data that lives at the leaves of the tree, and the commitment it's like a hash tree, So each node of the tree computes like a cryptographic hash of its two children. And, the commitment to all the data at the leaves is just the root hash of the tree. And to reveal a leaf of the tree, the authentication information is just like sort of all the nodes on the root to leaf path for that leaf, as well as the sibling node. And then to check that the information is valid, you just confirm that the hash of any two siblings in the authentication information, like indeed it equals the provided hash along the root to leaf path, and then finally that the root hash matches. So if you don't know what a Merkle tree is, that won't make any sense to you, but it's not a big deal. The point is that what the circuit winds up doing is just like taking kind of one piece of, authentication data, like for each copy of the subcircuit, and the subcircuit does like a pretty simple check. In this case, it'd just be evaluating a cryptographic hash function several times to sort of confirm that the information is valid. And then the aggregation function would just kind of compute AND, right? So like the C sub will output one or true if the authentication information was deemed valid, and zero or false otherwise. And aggregation in that case would just be, make sure everything output true. Yeah, so that's what a data parallel computation looks like. And I wanted to explain what why for such a computation, the wiring predicates are efficiently evaluatable. But let me pause here, see if there are any questions.
So I have a question about like the AND gate and MOD gate is just like it's just symbolic. Like I mean, in real world situation, are there like more types of?
Yeah, I mean there could be, and you see this.
I saw the hierarchs, I don't know, and Libra implementation. They have like 10 types of gates.
Yeah. So there are lots of papers that have played around with this to go beyond just addition and multiplication gates, and you can do it. It's just whenever you want to support another kind of gate, you have to modify the interactive proof to support it, but it's pretty straightforward to do. And you actually see this in practice. In fact, there's quite a bit of hype about it to be, I don't know, people are excited with, they call it Planckish arithmetization, turbo Planck, which is essentially using extended operations in the context of the Planck backend. But you can do it with pretty much any snark other than the linear PCP based ones like row 16. You can pretty easily support gates that don't just do addition and multiplication. I'll do an example right now. Let's say you wanted a gate that here's the simplest example. Like, let's just say rather than being able to multiply two things together, you want to be able to multiply three things together. Okay. So what you would do is you would introduce a new wiring polynomial. Let me call it like mult3 to indicate that the fan-in is going to be 3. And then that's going to take, rather than taking 3 gate labels as input, it'll take 4 gate labels as input. And it'll spit out 1 if B, C, D are the in neighbors of gate A. Sorry that you can't read my handwriting, or in neighbors of A. And A is a mult3 gate, a multiplication gate of fan-in 3. And, to spit out 0 otherwise. Right. And then, the analog then of mult, what the GKR protocol uses now is like this polynomial, and a sum over like BC BC, WI plus 1 total of B times WI plus 1 total of C. And that this now, like this changes now, rather than just summing over BC, you're going to have to sum over BCD and, have another term in there, and if you weren't, so that's how you would modify the interactive proof to handle a multiplication gate of fan-in 3. If that's a little confusing because you're now summing over more variables, let me give you a different example. Okay, so let's say here's a different example. So rather than computing the product of B and C, let's say you want the gate to compute the product of the squares of gate B and C. So now your sum would still be over, the same number, of variables B and C, but you would, so mult squared is, I'll call that the function now. But, now rather than computing WI plus 1 total of B times WI plus 1 total of C, you're just going to take the square of them. That's it. And the point is that by squaring them, you're only increasing the degree in each variable by, from 1 to 2. So, the assumption, the polynomial G of BC that sum check gets applied to which is now, mult squared twiddle I of Ri comma BC, Wi plus 1 twiddle squared B times Wi plus 1 twiddle squared is C. The degree in each variable has, it used to be 2, and now it is 3. It's literally in each variable only increased by 1. So you're getting now, the degree in each variable in B, because remember, B is like a vector of variables. I'm just using one symbol to denote a vector of variables. The degree in each variable of B went from, contributed by Wi plus 1, went from 1 to 2, because now that square is there. And then there's another degree coming from the wiring predicate. So you've only increased the degree by 50%. In terms of, so the proof length within some check has increased by sort of 50% per round, but you've managed to double you've potentially like halved the number of multiplication gates in your circuit, so there can be gains from considering these higher degree gates. Did that make?
Yes, and is there a reason to expand these gate types, or to just keep it only to have like add and multiplication?
Yeah. No, you can get concrete savings by considering the expanded gate types, and that's why some of the papers you looked at were doing it. So, for example, that's kind of what I was trying to get at just a moment ago when I was like, let's say your goal was to, just compute the product of a whole bunch of numbers. So your circuit was just like a binary tree of multiplication gates. Let's say the square of the product of a whole bunch of numbers. So if you literally just use multiplication gate, what you'd have to do, like you'd have a layer of gates like that does the squaring at the sort of at the top, I guess is something you could do. And then the binary tree of gates. And this is too detailed. So at a high level, by considering increase, a bigger gate set, okay, you can trade off some costs for other costs. So you might wind up, for example, like shortening the proofs and saving prover time. Would you even pay a price for it? So like, what in the little examples I just wrote out, in the whiteboard here, what you've done sort of when you apply the sum check protocol is you've slightly increased the proof length in each round, but you've also potentially reduced the size of your circuit, right? Because each gate is now just kind of doing more work. It's not just multiplying two values, but it's multiplying two values and squaring the result. So you're kind of getting like, more than one multiplication out of the gate. So, you paid a small price in terms of the proof length increasing a little bit in each round of the sum check protocol, but you've also potentially decreased the size of your circuit. So that potentially reduces the number of rounds, even though the total in the protocol, even though the proof length in each round went up, it also potentially reduces the prover time a bit because, the prover sort of has to do work for every gate of the circuit. And we've now made the circuit a little smaller. Yeah. So people are getting mileage out of these expanded gate sets today in practice. Is that clear enough? Sorry to sort of babble around it for a little.
I had a follow-up question. I was wondering if we could just zero in a little bit on proof length and just explicitly state what is getting longer in between these two examples.
Great. Yeah. So remember, in the sum check protocol, in each round, the prover sends, like in round J of sum check, the prover sends a univariate polynomial of degree equal to the degree of the polynomial sum check is getting applied to in the jth variable. Okay. So by, in the basic GKR protocol, you don't have these squares above Wi plus 1 twiddle B and Wi plus 1 twiddle C because the gate operations are just multiplication. So, it's just multiplying gate B and gate C together. So the degree of the polynomial that sum check is getting applied to in each variable for basic GKR is 2, right? So like consider each variable of B, you're picking up degree 1 from this multilinear wiring polynomial multi, but you're also picking up another degree 1 from this multilinear thing Wi plus 1, which B is getting fed into. Okay. So in basic GKR, in each round of sum check protocol, it's a degree 2 polynomial getting sent in each round. So that's 3 coefficients or 3 evaluations. That's what's required to specify a degree 2 univariate polynomial, right? Like A plus BX plus CX squared. But now if in this modified protocol, if you wind up squaring each copy of Wi plus 1 twiddle, the degree in each variable of the polynomial subjects getting applied to is now 3 rather than 2. Because, there's still, 1 degree coming from the thing that B and C are getting fed into. But now there's degree 2 coming from each copy of WI plus 1 twiddle because it's squared now. Okay, so in this modified GKR protocol with these squares here, supporting like this more powerful gate operation, which doesn't just do multiplication, but actually multiplies and then squares. The degree in each variable, the univariate polynomial set in each round now is degree 3. So rather than being, 3 coefficients, it's 4 coefficients. Okay, so like essentially nothing has changed in the proof, except there's 1 more coefficient getting sent in each round of some check. Did that answer your question?
I think so. And just to kind of affirm my understanding, at its base level, this is because the Lagrange interpolation of that polynomial is longer when you have higher powers in the thing it's trying to interpolate from. Is that fair?
Yeah. I mean, it's, and it's not specific, I guess, to Lagrange interpolate, right? Like, we've discussed there's sort of 2 ways you can naturally specify any polynomial. And for interactive proofs and snarks in general, like the Lagrange basis is often the most natural and nicest, but like any univariate polynomial, you can write down just its coefficients in the standard basis, a plus bx plus cx squared plus dx cubed. Or you could write it down in the Lagrange basis, which basically means just writing down its evaluations at, if it has degree, n at n, is it n or n minus 1 plus at n plus 1 points, I guess, 0, 1 up to degree 2 needs 3 points, degree 3 needs 4. Yeah, so it's n plus 1 points.
I think I understand. So basically just the space needed to represent the possibilities of the polynomial increases as we increase the degree.
Yeah. I mean, it's like a degree 4 polynomial has 5 coefficients, a degree 10 polynomial has 11 coefficients. So you increase the degree, you have to increase the description length of the polynomial. So so there's like trade-offs by considering these sort of higher degree gates. On the one hand, they're more powerful gates, so you can like make your circuit smaller in terms of number of gates. But on the other hand, when you like give the interactive proof that kind of captures the gate operations, you're going to increase the degree of the polynomials that the prover needs to, send to the verifier, so it's sort of a trade-off where like kind of the proof length sort of per gate might go up, but the total number of gates goes down. And so, but you often sort of come out ahead in many of the costs of the protocol by exploiting, slightly higher degree gates than, just bare addition and multiplication. So yeah, there's like a tension there, but you often get a win in practice depending on which cost you care the most about. I think like this Planck arithmetization stuff, which is not exactly just like taking circuits and going to higher degree gates, but it's quite analogous to it. It's something circuit-like, but not exactly a circuit. And then the degree of the operation of the primitive operations they allow in their circuit-like thing, they go up to degree 8, I think. So you don't want to go up to, degree like 1,000,000, because then, the cost of sort of each round, or like you're going to get like a 1,000,000-fold blow up in the degree of the polynomials you're dealing with, and that's no good. But like going up to degree 8, apparently, it might let them cut down the size of the circuit they're dealing with by, I don't know, like 4 or something like that. And it seems to be a win to have the circuit be 4 times smaller, even if you then pay some price for having degree 8 operations. Okay. Any more questions? All right. Well, thank you for the questions. I hope it was fruitful. And let me return now to this data parallel stuff. So I thought I drew, here it is. So so this is what a data parallel computation looks like. And again, like, a lot of things people are doing in practice are naturally data parallel. And so I want to actually tell you like what the wiring predicate of such a circuit looks like what this multi-twiddle polynomial would look like. So conceptually, what we're going to do now is we're going to break each gate label A, B, C into 2 pieces. So each of A, B, and C is going to conceptually be broken down into 2 different pieces. So let me call it B1, B2, and C1, C2. And like, I keep saying this to try to avoid confusion. Remember, each of these pieces is itself multiple variables, log of circuit size. So each of these is like log of number of gates at the relevant layer, many bits or many variables. Okay, and we're going to interpret A1 and B1 and C1 as sort of telling us like which gate within a subcircuit we're dealing with, whereas they just tell you which copy of the subcircuit you're in. The gate is. Okay. So, if the data parallel circuit, does the little subcomputation, applies it independently to a billion different pieces of data, A2, B2, C2 is like the binary representation of a number between 0 and a billion minus 1, right? Because they're just telling you which of the billion copies of the subcomputation we're dealing with, for this gate. Okay, so hopefully that makes sense. So in that case, we can express the multilinear extension of, the wiring predicate for the whole giant data parallel circuit as follows. So you take the multilinear extension just for the subcircuit. So let me call it mult sub I. By this I just mean the multilinear extension just for the little tiny subcircuit, and you feed into that the parts of the gate labels that are dealing with where in the subcircuit you are, and then then you just use basically the multilinear extension of the equality function. And so I'll explain what this is in more detail in a second, but applied to the 3 copy. Okay, so what this is it's the multilinear extension of the function EQ, which takes as inputs 3 binary vectors and outputs 1 if and only if they're the same vector. A2 equals B2 equals C2. Here they're binary. Here these are all in 0, 1 to the log number of copies of the subcomputation. Let me call that, I don't know, capital N. That's the number of copies of the subcomputation. 0 otherwise. And there's a very simple expression for this, like explicitly, which is just you product over each bit of the, so I'm saying there are log m of them, 0 to log m minus 1 if we're indexing from 0. And then it's just A2j times plus 1 minus each of them. And this is just tested, like conceptually, this is just testing sort of bit by bit. Are all 3 of these 1 or are all 3 of them 0? And unless they're all 0 or, all 1, this will die. Right. So the point is that, this maps 0, 0, 0 goes to 1 and 1, 1, 1 goes to 1. And any other binary vector goes to 0. So any other 3-bit vector gets mapped to 0. So that's the multilinear extension of the, kind of 3-bit equality function is this polynomial here. So yeah, that is in the data parallel setting, this is what the wiring predicate looks like. And sort of the point is that while the subcircuit itself could potentially have some crazy wiring pattern and so this term is expensive for the verifier to evaluate, linear time and the size of the subcircuit. We're thinking of that subcircuit as very small, but we're applying it many, many times. And so the kind of, if the number of copies of the subcircuit exceeds the number of gates in the subcircuit, then, the point is that the 2 labels are sort of dominating, it's like the circuit is kind of total size is dominated by the number of copies of the subcomputation, with each subcomputation being tiny, tiny, tiny. And the part of the wiring predicate sort of corresponding to the, which copy you're in is as regular as can be. And so evaluating it at around the point just takes time logarithmic in the number of copies, because this is just, for each one of the log number of copies variables in the sort of the part of the gate labels telling you what copy of the subcomputation you're in. It's just, what is it? 4 multiplications and 1 addition, and yeah, something like that. So anyway, the point is it's order log number of copies time to evaluate EQ twiddle at any point. Okay. Did that make sense?
I don't want to say 100% yes, but I think in parts, and I'm kind of looking to see where it builds up.
Okay. Yeah. So I guess I'd say, so in the text, there is a section which was not assigned on data parallel circuits. And it doesn't do exactly what I did here. It's sort of, but it's conceptually very similar. It has other optimizations on top of this for data parallel circuits. So you could look at that, but it's also, I probably should make this an exercise, that or just directly put this in the book itself. So yeah, I don't know. This is the sort of thing where it is good to go off on your own and work it out, I guess. Remember, whenever somebody claims here is a really nice expression for the multilinear extension of something, the 2 things you always need to check are that, the expression that they're giving is a multilinear polynomial. And the other thing you need to check is that it agrees with the function being extended at all Boolean inputs. So, you really just need to look at this expression I've written here observe that it is multilinear, which is just immediate because, the mult sub twiddle thing is multilinear by definition, and EQ twiddle is multilinear by definition, and each variable gets fed into only one of them. So the whole thing is degree 1 in each variable. And then the other thing you have to check is that, you feed in like literal gate labels, like that is binary values, into this expression, and it actually does spit out 1 if and only gates, B1 comma B2, C1 comma C2 are indeed the in neighbor of gate. And the point is, like in the data parallel computation, that is the case if and only if, will indicate these gates are all in the same copy of the subcomputation. And moreover, within that subcopy, gate B and C are the in neighbors of gate A. So that is the way to verify this claim, and it's a good thing to do offline. Yeah. You see someone's typing in the chat. Well, maybe I'll just sort of babble for a minute while it stopped. Okay, I'll keep an eye out on the chat. Yeah, so I actually think there's like quite a bit of confusion about this point in the literature. So, I guess I want to be a little careful what I say, but like Starkweather's big thing is like sort of always dealing with kind of circuit, like they don't use the term circuits. They talk about air, algebraic, and immediate representation. But anyway, their big thing is like always avoiding a verifier having to do work proportional to the size of the computation. And the way they're doing that is kind of, that they always generate something like a circuit which has repeated structure. Okay, but my point here is it's not unique to, the probabilistic proof systems that Starkweather is using, right? Like pretty much anything out there with some exceptions, but like certainly anything based on the GKR protocol and related techniques is going to have the same property that, if your circuit has repeated structure, then the wiring polynomials are also going to be highly structured in a way that allows the verifier to evaluate them at, the points required very quickly, in time substantially sublinear in the size of the whole circuit. So that's the point I'm trying to make, and I'm spending time on it and trying to be clear about it, because from what I can tell, there's confusion about, how the various approaches to snap design compare in this regard. A lot of them have this. And yeah, as I was sort of hand waved before, another thing, if your circuit is totally irregular wiring pattern, so evaluating these wiring polynomials would be expensive for the verifier. Another thing you could do is sort of have the prover like someone cryptographically commit to these polynomials like in a pre-processing phase. And then, the prover just needs to kind of reveal the evaluations of the committed polynomials online, and that can be much faster for the verifier than just doing the computations of, the evaluations of the wiring polynomials itself. And people will use terms for that technique. They'll sometimes call it holography, which is like a needlessly, a sophisticated sounding name for, a very simple idea, or they'll sometimes call it computation commitments. Okay, so that's everything I want to say about really the GKR protocol in general. We could pause for questions again, or I could spend 12 minutes sort of talking about, I could say a little bit about chapters 5, 6, and 7 at a high level in 12 minutes. I will pause. Does anyone want to ask anything else? Cool. So yeah, that takes us through the end of chapter 4 of the book. So chapter 5, I believe, is onward. Yeah, great. I'm excited. I hope you are too. So on something called the Fiat-Shamir transformation. And look, this is something that's really interesting and important. And in fact, there were major security flaws in a bunch of deployed snarks recently because they implemented this incorrectly. But for now, I just want to say you can, for understanding purposes of the snarks we're going to see moving forward, you can just treat this as a black box. So it's just a way to take any public coin interactive proof or argument and turn it completely non-interactive, to just like pull the interaction out of it and make the proofs just static strings. Now, if you start with an interactive proof, that means it's information theoretically secure. It's sound even against provers that spend an unlimited amount of time trying to break the crypto system. I'm trying to convince the verifier to accept an incorrect statement, a false statement. The Fiat-Shamir non-interactive protocol will be an argument, and basically in practice, in like the real world instantiation of the Fiat-Shamir protocol, if you can kind of break the collision resistance of a hash function, you actually need the hash function to act like a random oracle, whatever. Anyway, if you could break some hash function, some kind of cryptographic hash function, if you could break it in some sense, you could generate convincing proofs of false statements. So you no longer get information theoretic security in the real world, but you do get a non-interactive protocol. So yeah, for now, you can just view fiat Shamir as a black box transformation. It'll take any public coin interactive thing and turn it into a non-interactive argument. I will answer the question in the chat in a moment. Let me remind you, what is a public coin interactive protocol? That is a protocol where essentially the verifier's messages to the prover are just like random coin tosses or random field elements or something. And so like every time the verifier like more random coins, that is like makes another random selection, like that randomly chosen value is immediately revealed to the prover. And like that's the only information the verifier sends to the prover over the course of the protocol. Okay, so there's a couple questions in the chat. So one is this the role of reference strings in applied settings? So we should talk about what you mean by a reference string for a moment. So there are two kinds of reference strings. So one is a structured reference string, which basically means there's some kind of trap door and for some like toxic waste that is sort of the reference string is structured in some way. And like if you kind of know this piece of secret information, this trap door that underlies the structure, then you could successfully like cheat the proof system and break soundness and identify convincing proofs of false statements. And then there's unstructured reference strings, and the fiat Shamir transformation does contribute to the unstructured reference string. So basically, in that, to apply the fiat Shamir transformation in practice, the prover and verifier simply need to agree on a cryptographic hash function. And for theoretical purposes, that's modeled as a very short, unstructured reference string. It's just a random short string that tells you the cryptographic hash function used. Like in practice, when people use SHA-256 or whatever, SHA-3 or, Blake 3 or whatever, they've sort of agreed kind of out of band, what the hash function is. And then you don't really need even the unstructured reference string sort of as a practical matter, kind of the decision to use SHA-3 sort of acts as the unstructured reference string right there. So hopefully that answer makes sense. And some of these arguments that do wind up using the fiat Shamir transformation, there are other contributions to the reference string beyond the hash function that's going to be used to implement fiat Shamir. But the only information you need just for the fiat Shamir part of the protocol alone is just they have to agree on a cryptographic hash function. Okay, so hopefully that made sense. Okay, now, why do we go from an IP to an argument when we apply fiat Shamir? Are IPs even possible after applying the fiat Shamir transformation to an IP? So here's one answer to the question, which is a non-interactive proof, meaning information theoretically secure proof system that's non-interactive. That's just NP, non-deterministic polynomial time. That means, static proof strings where now there's no verifier randomness. So, the verifier soundness error is either 0 or 1 kind of. And so NP proof systems are just, not believed to be all that powerful certainly in the succinct setting, right? So like people basically define succinct arguments to mean like the proof length is shorter than what you would get out of an NP proof system. So almost tautologically speaking, a succinct argument, or a succinct non-interactive protocol cannot be a information theoretically secure proof system. Okay, so that's why you'll never see somebody talk about like a succinct non-interactive proof. There's no SNPs out there. There's only snargs and snarks, succinct non-interactive arguments. Yeah. So like the whole point, or one of the big points of these snarks, is to get the proof length really short so that verification is really, really fast. And you just like almost by definition, like you're going to only get an argument. You're not going to have information theoretic security for that. Did that make sense?
Yes.
Great. And if you actually read the fiat Shamir chapter in the book, it'll describe various natural attacks on the fiat Shamir transformation. And if you're just given unlimited time, unlimited attempts at, to evaluate the cryptographic hash function at this point. And like, if you're not happy with the result, evaluate it at another point, and then another, and then another. Like, you'll eventually find a convincing proof even for a false statement. If so, yeah, just check out the chapter and you'll see more about how, a computationally unbounded prover can attack fiat Shamir transforms protocols. And I do discuss in the chapter, by the way, like the issue that led to the bugs. It's a known issue, like it's led to bugs in the past. And so I made sure to highlight it in the book so that, it doesn't keep happening over and over again. Okay. Is there a reason to use newly developed CI hash families rather than SHA-3? No. So these newly developed CI hash family is something discussed in the book. So you can read the chapter if you want to know what that means. These are theoretical things used to just make security proofs go through. Like, if you look at the CI hash families that people have come up with, that are, so CI means collision and correlation intractable. Exactly what that means isn't important, but people have been able to show that, certain applications of fiat Shamir are secure in the plain model, meaning no random oracles, when instantiated with CI hash families. And they've then identified CI hash families based on like learning with errors, which is a cryptographic assumption people like these days. They're not like very fast hash functions. So it's quite reasonable to conjecture that like real world cryptographic hash functions like SHA-3 like are CI, but we don't have any like formal justification for that. So yeah, I mean, is there a reason to use the newly developed CI hash families in practice? I mean, I guess if you want like more theoretical justification for security, but like your practicality is really going to go out the window, I think. I don't believe, I don't want to make overly strong statements. Like, the fiat Shamir transformation tends not to be the computational bottleneck in any of these protocols. So maybe like even using very expensive hash families is fine. But yeah, like these CI hash families people have developed recently, they often, the original one have the flavor of fully homomorphic encryption, which is like way slower. FHE at least is way slower than any zero knowledge proofs, really. So yeah, I would just say like, just apply fiat-3 in practice and like take the new papers about correlation intractability as like some kind of loose justification for security of the resulting protocol. And just to be further clear, like the results people have about fiat Shamir being secure in the plain model when instantiated with CI hash families, those results don't apply to snarks. They apply to interactive proofs and that are then fiat Shamired, and they apply to some non-succinct arguments. But it's like a major theoretical open question to get similar results for snarks. But like the practitioners are just like kind of totally happy to apply fiat Shamir and say, oh, this is not where people are going to break our snark in practice. Okay, follow up. It always looks a bit strange for me because we know that a protocol is IP, but we do not know if it's an NP. Is it possible that after applying FS, we were able to prove the same but an NP? Yeah, so what's happening is just that the fiat Shamired interactive protocol, it's not an NP protocol because it's not statistical, it's not information theoretically sound. That's it. So you take an interactive proof, you fiat Shamir it. What comes out is non-interactive, but it's not a proof anymore in the sense of it's only an argument now. So it's not an NP protocol. Okay, so I know we're out of time. I should probably just stop here. I don't know, maybe I'll just tell you what 6 and 7 are about. If you need to drop off, go ahead, because we're just obviously going to repeat this in future weeks. So chapter 6 is about front ends, basically like how you turn computer programs into like circuits or circuit satisfiability instances or R1CS instances that then one would apply snarks for snark. People will develop snarks for circuit sat or R1CS satisfiability, but to actually use that snark, you need a way to turn the computation you care about into a circuit satisfiability instance or an R1CS satisfiability. So it talks about some of the basic techniques to achieve that. And like, if you're going to take one thing away from that chapter, it's like, just as a theoretical general statement, you can take any computer program running in time t, and you can turn it into an equivalent circuit satisfiability instance where the circuit has size like t times polylog t. So pretty close to t. right? So like evaluating the circuit gate by gate is like not going to be that much more expensive in a theoretical sense than just like running the computation, with no, just directly on your, laptop. And by equivalent circuit satisfiability instance, what I mean is, if the computer program outputs Y on input X, then for the circuit satisfiability instance, like there exists an input, like what's called a witness W to the circuit that causes the circuit to output Y. It's like an if and only if proposition. So, right, like if the computer program outputs Y on input X, that's equivalent to there being a witness W that causes the circuits to output Y when applied to input X comma W. So the input to the circuit satisfiability instance now sort of has two parts, like the public input X and like an extra part, which we call the witness or non-deterministic part. And sort of the existence of a witness causing the circuit to output Y is equivalent to the original computer program outputting Y. And yeah, then chapter 7 tells you how to get succinct arguments. And in fact, snarks tells you what a snark even is for circuit satisfiability. So like to just give two more sentences on this and then we'll wrap up for the day. Like the kind of the naive way to give an argument system for circuit satisfiability, or even an interactive proof for circuit satisfiability, right, is to have the prover send the witness to the verifier, right? So the prover claims, hey, like there exists a witness W that causes the circuit to output Y. And like the trivial proof system for this is for the prover to send the witness to the verifier and then prove, like use the GKR protocol to prove that the circuit C evaluated on input X, comma, the witness spits out Y. And that works. But the problem is we consider the proof to be too long because the prover had to send the witness to the verifier. And we're thinking of this witness as potentially being very large. So a succinct argument for circuit satisfiability will avoid that expensive step of like the prover sending the whole witness to the verifier. And essentially what happens is you kind of try to cryptographically mimic the naive approach. So rather than having the prover send the whole witness to the verifier, we have the prover like cryptographically commit to the witness, but by sending a commitment that's very, really small, like a tiny commitment, like just a single like Merkle hash value or something, like a single cryptographic hash output, like to bind the prover to the witness. And then the prover winds up sort of proving that like it knows an opening of the commitment, so that if you then evaluate the circuit on the opening, it does indeed evaluate to Y. And so you kind of wind up combining like the GKR protocol or some other protocol for circuit evaluation with the cryptographic witness commitment. And in total, you wind up like avoiding the prover ever having to explicitly send the witness to the verifier. And that's how you get succinctness at a very, very, very high level. So I guess in the coming weeks, we will talk about the details of those cryptographic commitment schemes and it just explain more rather than two very quickly stated sentences about how these things work. Okay, so 2 questions in the chat. Can we say that NP is a subset of argument systems, is a subset of IP? So yeah, so NP proof systems are weaker than IP proof systems, which are weaker than argument systems. So, right, weaker meaning if a problem has an efficient NP proof system, then it also has an efficient interactive proof system in the sense that, the interactive proof system is just non-interactive, but a proof system like, information theoretically secure. And if it has an efficient interactive proof system, it also has an efficient argument system. In fact, if you're willing to use the Fiat-Shamir transformation, it has even an efficient non-interactive argument system. So the hierarchy of power is, non-interactive information theoretically secure protocols can only be weaker than interactive information theoretically secure protocols, aka interactive proofs, which can only be weaker than argument systems, whether they're interactive or non-interactive, just because you can always take an interactive argument and make it non-interactive by using, with the major caveat that only applies if it's a public coin argument system. Okay, but like essentially with one exception, which is not practical anyway, all of the argument systems we cover in the book are public coin, so you can always apply Fiat-Shamir. Okay, and then the last question, can we then? Oh, sorry, that's just a repeat on a more nicely typeset version. of your question. Yeah. So I hope that made sense and answered the question. Okay. I have just a couple more minutes if anyone wants to get in one last question. Otherwise, we'll call it a week.
Page 109, the fourth paragraph. So it says the scheme is binding in the following sense. Is the whole paragraph just saying if we want to break this polynomial commitment scheme, we have to find a collision for the hash function?
I mean, what's happening around that point in the text is Merkle trees were introduced. Okay. Merkle trees, if you cannot find a collision in the hash function used to build the Merkle tree, then Merkle trees are binding in the sense that like once the committer sends the root hash, to the recipient or the verifier of the commitment, the prover or the committer is bound to a fixed string, meaning if the verifier says, hey, tell me the ith entry of the string that you have committed to, right? The prover has no choice at that point but to answer consistent with, whatever string it's now bound to. So yeah, it's saying like the only way to break that binding property of the Merkle tree is to find a collision in the hash function. But to get a polynomial commitment scheme, you need more than that, right? Because the Merkle tree itself does not guarantee that the string the prover is bound to is actually the list of all evaluations of a low degree polynomial. It's some string, which you can always interpret that as the list of all evaluations of some function. Okay. But like the Merkle tree itself doesn't tell you anything about that function. It's just some function. So the polynomial commitment scheme sketched in chapter 7 combines the Merkle tree, which it just binds the prover to, some vector, which we can always interpret as the list of all evaluations of some function, with a low degree test that basically, allows the verifier to become confident that the string or vector, as synonyms in this context, that the prover is bound to by the Merkle tree is in fact the list of all evaluations of a low degree polynomial. You put these two guarantees together and that gives you the polynomial commitment scheme. The prover is then in fact bound to not just an arbitrary function, or, more precisely, the list of all evaluations of a function. But in fact, that function is guaranteed to be more or less a low degree polynomial, up to this whole, is it exactly a low degree polynomial or just close to one? Did that clarify things at all?
Yes, and the possibility of the low degree test passing is dependent on like what?
Yeah. So typically, just the size of the field. Like, so it's sort of similar to like the GK like interactive proofs themselves, where basically like kind of the soundness error is inversely proportional to the size of the field. So like the bigger field you work over, like the luckier the prover has to get to like trick the verifier. So it's basically analogous for these low degree tests. So essentially, you apply one of these low degree tests over a big enough field and like the probability the prover really is bound to a string that is very far from any low degree polynomial, but still the prover manages to pass the low degree test. Like that probability can be made like, incredibly close to zero. It's just that actual low degree tests, like the work the prover has to do to run the low degree test, very like impractically expensive. So that's why subsequent chapters sort of analogs, like different polynomial commitment schemes, some of which are low degree test like, but not, not they'll leverage interaction, whereas low degree tests are basically non-interactive to improve these bad prover costs and when the prover tries to apply the low degree, run it as part of the low degree test. Does that make sense?
Yes. And how exactly does extraction of extractor algorithm work?
Yeah, so we have to talk about that more in later chapters. I mean, basically so for the kind of polynomial commitment scheme given in chapter 7, and there's a extractability result for Merkle trees, which basically kind of says we should just punt that till later. Like there are known ways to take like a prover that constructs convincing proofs for snarks that use these like Merkle tree based polynomial commitment schemes. There's like a known procedure to kind of watch how that prover works and kind of identify the string that the prover is bound to efficiently just by kind of watching the prover build the proof. And sort of once you identify the string that the prover is bound to, it turns out like the witness for the circuit satisfiability instance that the prover is making a claim about must just be like living in the string, must be embedded within that string. So that probably didn't make much sense. We should discuss this further in probably chapter, I don't know, 8 or 9 or 10 or something. Yeah, unfortunately, I can't say much more than that now. Certainly not when I have to go.
Okay. Thanks.
Okay, thanks everyone. I guess I should wrap up or I'm going to get in trouble. So thanks as always. Thanks for, letting me blabber for an extra 15 minutes. I always appreciate it. And yeah, have a great weekend. Look forward to seeing you next week.
Thank you. Take care.
Have a good one.
Thank you.